I press this blue video.
You just click on the video, yeah, where it says stop video.
I don't see stop video.
Bottom left-hand corner of your screen.
Do you have video now?
Yep, we still see you.
Well, there's nothing. Oh, wait, leave meeting. Stop video. That's the top of my screen. Okay.
There you go.
How's that? Okay.
Sounds good. All right, and I'm going to share my screen with all of you so I can show you some fun stuff. And I thought we would start this evening by watching one of the trailers of Interstellar. So let me bring that up. It's just about 2.5 minutes, and then we can start this session of Sci-Fi Explained. So here you go.
What are you going to do with it?
I'm going to give it something socially responsible to do.
Can't we just let it go?
This thing needs to learn how to adapt, Murph.
Gang, let's mask up.
Like the rest of us. This world's a treasure. It's been telling us to leave for a while now.
Your daughter's generation will be the last to survive on Earth. You're the best pilot we ever had. Get out there and save the world.
Everybody ready to say goodbye to our solar system? To our galaxy? Here we go. We're here. Want to get down fast, don't we?
Actually, we want to get there in one piece.
Hang on. Our mission does not work if the people on Earth are dead by the time we pull it off.
Well, we got this far, farther than any human in history.
Oh, not far enough.
Make it count.
Where's the mountains?
Those aren't mountains. They're waves.
I'm not gonna make it!
Yes, you are. Yes, you are.
You might have to decide between seeing your children again and the future of the human race.
We'll find a way. But we always have.
All right, very sensational. So that's Interstellar. That is the movie we're going to be chatting about this evening. And so let me just kind of set the stage a little bit for what some of the science was that they tried to portray in this movie. Obviously from the trailer we just saw, there's some stuff about black holes and wormholes, some stuff about time paradoxes and time dilation. So a lot that has to do with Einstein's theory of general relativity and the consequences of being in really, really strong gravitational fields, such as around a black hole. So first, let me just say a little bit about black holes and wormholes, Einstein's theory of general relativity, and then we can start picking apart what they actually got right and what they didn't get right in the way this all got portrayed in Interstellar. And feel free to ask questions as they come up for you. I definitely want this to be an interactive experience. And make sure we get everyone's questions answered by the time we're all done. So black holes are absolutely real. We now have direct observational evidence of black holes, and that just happened for the first time last year. But they were first theorized over 100 years ago as part of Einstein's theory of general relativity. What that theory showed is that there can be areas of space-time that have such strong curvature, which is what general relativity really tells us, that space-time curves because of mass moving through it. And then that space-time tells mass how to move through it. That those curvatures can be so strong in some areas that you can enter into that curved space-time but never leave. And that's because that curved space-time can have an escape velocity greater than the speed of light. And from Einstein's special theory of relativity, we know that there's no way to accelerate to the speed of light. It just can't happen. And so a black hole is a physical object in space that has an escape velocity greater than the speed of light.
I have a question.
Please, Stuart, yeah.
Okay, so why is the speed of light, was that arbitrarily set?
Great question.
And then
So-
show experimental data, and it just
Yeah.
is because it is? Like, in other words, why couldn't it be, instead of 186,000 miles a second, why couldn't it be 921,000 miles?
Right. So the number itself is something built into the structure of this universe. We don't know why the value is what it is, but there are some great films on YouTube that I can send you, which discuss the fact that the speed of light is really not about light at all. It's really about causality. And that's what comes through really strongly in special relativity and general relativity as well. This idea that for there to be universal agreement on any event in the universe, there has to be some way that we can all agree on when something happened and what event caused other events. And it turns out in the normal way that we do that on Earth, by measuring velocities relative to the ground not moving, doesn't work in space-time. You have to use these very special transformations, these mathematical transformations, so that everybody agrees on when something took place and how fast something is moving. And it turns out that the universe does have a fundamental limit on the speed of causality. The greatest speed in which one event can influence another event. And it turns out that the extent that any object can do that is relative to its mass. Only massless objects can move at that top speed of the universe, the speed of causality. And light is massless. And so light can actually propagate through space at the maximum speed allowed for causal relations in the universe. And that just happens to be there about 300,000 meters per second. But it really doesn't have to do about light. It's just that light is a massless particle. All massless particles can travel up to that speed. But any particle of mass can only travel at some fraction of the speed of causality. And the more massive you get, the more energy it takes to accelerate that object up close to the speed of causality, but you can never actually get there.
So I guess we'll get more into this discussion when we talk about the science of wormholes a little bit.
Yeah, so black holes are real. We've actually taken pictures of the accretion disks around black holes now in M87, big galaxy not too far away in the long scheme of things. And the Event Horizon Telescope is actually working on getting an image of the black hole in the center of our galaxy right now. And so we think they're probably a supermassive black hole in the center of every huge spiral galaxy in the universe, and maybe in the center of every galaxy in the universe. So those are the really big ones. There are also smaller black holes called stellar mass black holes. And as the name implies, they're much closer to the mass of stars. in the range of 20 to 100 times the mass of a star, compared to the supermassive black holes, which are millions or even billions of times the average mass of a star. And so the black hole that we have portrayed in the movie Interstellar has the mass of about 100 million suns. So it's one of those supermassive black holes, presumably in the center of the Milky Way galaxy. So that's science. Wormholes are also theoretically possible. They were another prediction that came from solutions to Einstein's original equations of general relativity. However, we have no observational evidence of wormholes existing. And in fact, we think for them to exist, we would need this exotic type of matter that has negative mass, which may or may not actually exist. So although the math bears out the existence of wormholes, and it may be possible to actually build one at some point if we could actually get our hands on this exotic matter that has negative mass, we've actually never seen anything like that in the universe. But it would be the inverse of a black hole. It would be an object that you could only exit from, that there would be no way to get into. There would be a net outward force. Gravity would be inverted compared to in a black hole where the force of gravity brings you in towards a black hole. And in this movie, there's also a wormhole. And so, you know, they created the images based on scientific theory. I can show you a little video that just takes a few minutes that shows you a demonstration of what it might actually look like to travel through a wormhole without a lot of the extra extravagance that got put into it with the movie Interstellar. But they really are, at this point, science fiction. There may be some advanced civilizations that learn how to construct these things once they figure out what exotic matter is, but we're not there yet. Some people postulate that potentially whatever makes up the dark energy in the universe might actually be this exotic matter that actually has negative mass, but we don't know that yet. It's pretty much just speculation. And there are lots of problems with traveling through wormholes. It turns out keeping them open is pretty difficult. And we can watch a little movie about that if you're interested later on. So that's kind of the basics of relativity. This idea that space, it becomes curved in the presence of mass. And when you have a lot of mass, space curves a lot. So much so that it can create objects that have escape velocities greater than the speed of light, like a black hole. The other really interesting thing that occurs in strong gravitational fields relative to weak gravitational fields, like on Earth, is this thing called time dilation. And it's been portrayed in this movie and in lots of others. Time dilation is real. We actually have to fine-tune our GPS satellites to keep track of time dilation because of how fast they're moving. So it's not just about being in a strong or weak gravitational field, it's also about velocity as well. But in the movie Interstellar, they showed gravitational time dilation. So the idea was that the astronauts who were orbiting close to this black hole called Gargantua in the movie had time that was moving much more slowly relative to people on Earth. And that actually is real. We know that as you get into stronger and stronger gravitational fields, time does slow down. You don't actually notice that happening when you're in that gravitational field. But then when you leave that gravitational field, you find that observers who had been in weaker gravitational fields experience time passing much more quickly for them compared to what you did. So that general idea is accurate in the way they portrayed that in the movie. We'll get back to whether their portrayal was precise or not in a little bit. One other thing that the movie talks about, which I think is pretty interesting, is the idea of time paradoxes. And this does get introduced through the use of wormholes. So the idea in the movie was that somehow humans evolved to be technologically advanced enough to build this wormhole, which they then placed somewhere that could be found by humans in the past, which would then help them leave the Earth, become technologically advanced to actually build this wormhole in the future. And it turns out that wormholes actually do allow those types of time paradoxes to take place, which is why some physicists think they can't actually exist in the first place. But if we do figure out how to build them, they can actually introduce these time paradoxes, where you could potentially travel through space-time to events that we would today call in the past or in the future. And that gets portrayed a little bit at the very end of the movie in the Tesseract. So the Tesseract is this multi-dimensional space, way more than 3 or 4 spatial dimensions, where time becomes a physical dimension that you can actually see in front of you. There are actually mathematical theories that suggest that might actually be possible, and that our universe might actually exist in that way. The dimensions are just curled up so tightly that we don't have access to them. But at some time in the future, we may figure out how to have access to them. And just as we can move through the 3 dimensions of space, we might actually be able to traverse a dimension of time and actually see our full lives laid out, happening simultaneously in front of us. And so we wouldn't actually be moving to the past or the future. All events would just be present. So there's this unending now. And that's kind of the idea of the Tesseract that they showed in the near the final scenes of the movie. How you actually get into a Tesseract from falling into a black hole, that's just science fiction. But it was the only way they could actually bring Matthew McConaughey's character out of a black hole. That doesn't happen. There is no way to get outside of the event horizon of a black hole once you have crossed the event horizon. That just doesn't happen unless there is a multi-dimensional Tesseract there waiting for you, which may or not be possible to actually build someday. So those are all the big themes that get portrayed in the movie. Before we start tackling...
Oh, I have a question.
Yeah.
Was there some connection between, I don't remember every nuance of the film, but these people from the future that put the wormhole there near Jupiter or Saturn, wherever it was,
yeah,
they also responsible for putting the Tesseract in the black hole?
That's right. Yeah, they figured out a way to connect that multi-dimensional space somehow with right at the edge of the event horizon of the black hole. They don't really talk about how they do that, but I guess if your technology is sufficiently advanced, you can do that kind of stuff. That's definitely science fiction. However, as I said, there are mathematical underpinnings of that type of multi-dimensional space. It's actually called bulk space or hyperspace. You can look it up on Wikipedia and read all about it. It's interesting stuff, and it may actually be what this universe is. If you've ever read about string theory, some formulations of string theory suggest that there might be as many as 11 folded up dimensions that we don't have access to. So who knows what the universe is really like that we all inhabit. We may be prisoners to a 3-dimensional universe that actually has way more spatial dimensions and temporal dimensions that we can actually access in our limited experience. So that's kind of like broad picture of all the different scientific concepts that are covered in the film. Turns out there's already been a lot of commentary on this. Neil deGrasse Tyson has weighed in, as has the astronaut Chris Hadfield. Kip Thorne, another astrophysicist who actually consulted on the movie. And a lot of his theories are what are modern day depictions of black holes are based off of. So it was pretty cool. He was actually an executive producer in the film. So he consulted throughout the whole thing. I watched a little interview with him and the director, Christopher Nolan, and apparently they went back and forth throughout the whole making of the film, deciding on what parts of the film were actually close enough to science to put in and which parts just had to be tossed out because they were absolutely, completely science fiction. And so there is that to be said about the way this is all depicted. It really was the brainchild of Kip Thorne, probably one of the most brilliant physicists alive today. But let's start with the black hole itself, this black hole gargantua. And it's got this really bright ring around it that's distorted. And that's the accretion disk. And so the accretion disk is this big spiral of material that is accumulating around a black hole. Hey, Matt. Accumulating around a black hole, which eventually falls into the black hole. But as it does accumulate around the event horizon of the black hole, it moves very rapidly around the black hole. It heats up and gives off a lot of light. So that's that big glowing disk that we see around the black hole in the movie. There's some great explanations of how that disk appears the way it does in the movie, and I can send out the links to those, but they're both from the website Veritasium. This guy does an absolutely brilliant job of explaining why black holes look the way they do in the movie Interstellar, and why they look the way they do in the pictures that we just took of them for the very first time. And what's actually going on is what's called relativistic beaming. The light from the accretion disk on the back side of the black hole from our perspective gets warped up above the black hole to look like what we saw in the movie Interstellar. And so that depiction is actually probably a lot like a black hole would actually appear if we were up close and personal to one. If we have time later on, I can show you some pieces of these films, and you can actually see the details about why they look the way they do. But this accretion disk is pretty interesting because it's glowing, and according to the science in the movie, it has the brightness of the sun. So that means it's a pretty big accretion disk, and it's given off a lot of radiation. And the thing to understand about this accretion disk is that the orbits in the accretion disk and around it are totally unstable. So there is no way that there would be planets orbiting near the accretion disk of a black hole. And if they were, they wouldn't be there for very long. They'd get ripped apart and pulled into the black hole. So the fact that the whole future of humanity hinges on them inhabiting these mythical planets orbiting around the black hole is complete bunk. There is no way that there would be planets right there. Why they decided to do that, I'm not sure. Mike Brotherton actually pointed that out to me, who just gave the speaker series presentation on Friday. He actually wrote a brilliant blog about the movie Interstellar, and that was one of his biggest critiques, that there's just no way that there would be stable planets around the accretion disk of a black hole. It just wouldn't happen. The orbits aren't stable, and the radiation would be intense, so there'd be huge temperature fluctuations on the planets. And so, yeah, that's just not possible in the way they portrayed it, at least. As Mike Brotherton pointed out, it would be orders of magnitude better to be on Earth with a terrible blight wiping out food for the entire planet than to be on a planet orbiting around a black hole. So they kind of missed that one. The other thing that is not too scientifically accurate about the way they portrayed the black hole is the extent that time dilation happened. If you recall in the film, they spend just an hour or so on one of the planets, the water world, in around the black hole, and then they return back to their spacecraft farther out, and something like 7 years had passed, or something similar to that. For that amount of time dilation to actually occur, they would actually have to have been about 100 meters away from the event horizon of the black hole. And you can't really fit an Earth-like planet in 100 meters. So the way they portrayed time dilation was incredibly exaggerated from what would have actually happened in those planets that close to a black hole. To actually have time dilation that much, the planets would have had to have been much, much closer to the black hole itself, which is impossible. So they took some liberties there as well. But the idea of time dilation is totally legitimate. Couple other things about gravity that just, from my perspective, didn't make any sense. You might remember that there's this hovercraft that connects to their spinning space platform, and the hovercraft first blasts through space, and then goes into the atmosphere of these planets, lands, and then takes back off from those planets and goes back to their rotating spacecraft up in orbit. There's nothing known to physics that can do that. If you also remember in the film, they leave Earth in this giant rocket, right? So that's how we get things into orbit. You need a huge amount of propulsion to escape the gravitational pull of even an Earth-sized planet. And so they're escaping the gravitational pull of an accretion disk of a black hole in a hovercraft? I don't think so. The idea is that maybe technology is sufficiently advanced and they've actually figured out ways to create incredible types of propulsion that just look like little air jets coming out from those hovercraft. But we have no technology known to us right now that would allow us to actually both cruise through the atmosphere of a planet, land, take off, and go through space. That just doesn't work like that. So that's a big problem.
How do they, I thought that when they went through the wormhole, they had the same craft that they used to then land on these planets. So
yeah, so they're
timed.
So they're two different craft. I think I got some pictures ready to show you guys of this. So one craft are their little hovercrafts, and the other one is their revolving platform. Let me bring these up here.
But if they went through the wormhole in the year 2067 or whenever supposedly they did.
Yeah, and they went.
They had the technology to create this landing craft with this great propulsion.
Yeah, presumably that's what they were able to do. But how they can
through the wormhole.
Well, so no, the spinning spacecraft went through the wormhole, and all the little hovercrafts were attached to it. They had several of the little hovercrafts attached to the spinning platform. I think I've got a picture of both of these I can show you here. Let's see here.
Sam,
yeah.
The YouTube image that's in front of us now, is that Kip Thorne explaining the black hole image?
It's not, no. This guy, I just blanked on his name. He's a guy who runs a website called Veritasium. He's a brilliant physicist and science educator and does an awesome job at explaining pretty complicated phenomena. So this is a great video to check out to understand black holes. So here's a picture of the hovercraft here. So this is what they landed on. Specifically the water world and the ice world as well. And then let's see if I can find.
You can't see the image.
You can't see it.
No, we're still on the YouTube guy.
Okay.
Yeah.
Let's see if this works. How about that?
No. Oop.
There we
Yes.
go.
Yeah?
Yes.
Yeah.
Yes.
Okay, thank you. So there's the hovercraft that they landed on the world's presumably orbiting around the black hole. And then the spinning spacecraft, I don't think I have a close-up shot of it. Here's one from a distance that also shows the black hole. I'll show you this in just a second here. You really can't see anything there. See if I can find something better. Let me go back to that other share. Let's go back here. You see that website again now?
Yes.
All right. So let's
DuckDuckGo.
rotating spacecraft on Interstellar. Let's see. Oh yeah, here it is. I think this is. Oh yeah, there we go. Yeah, so that's what it looked like. That's their rotating spacecraft, and it's hard to see where the probes, the little hovercrafts, were attached, but oh yeah, so there it is. You can see it in that one a little bit better. Yeah, so the hovercraft was positioned in the center of it there. And then that big rotating spacecraft is what they took through the wormhole. So yeah, so the hovercrafts don't really work, and the way they portrayed time dilation doesn't really work. So they took some liberties with those gravitational effects. You might also remember a scene in the movie where there were these tractors that mysteriously ended up back at the house where Matthew McConaughey's character lived. Let me bring that part of that scene up for you. Can you see that now?
No.
No?
Yes.
Yeah.
Now you can?
Yes.
So if you remember in the film, all the tractors kind of mysteriously migrated back to this house as if there was some weird gravitational phenomena pulling him there. But gravity doesn't work like that. Even though there was some mysterious gravity happening in the library of their house, if the gravity had been strong enough somehow to cause malfunctions with those tractors, it would have caused malfunctions in everything else just as massive or less than massive. So everything would have been pulled towards the house if it was gravity doing that. So there's no reason to believe that the tractors would have been attracted in that way and not everything else. So that was just kind of bogus in that way. The other interesting thing about gravity was that it was shown to allow some type of communication between the different dimensions that were portrayed in the Tesseract. And so there was a scene, several scenes where you keep coming back into this library. At first, books get mysteriously pushed off the shelves. And the gaps that they make in the bookshelf in Morse code spell out don't go or stay, something like that. I can't remember. And then there's the dust that comes down through the bookshelf, which gives the GPS directions for the secret NASA base, which they interpret. And then finally, at the end of the movie, he's able to gravitationally send a message in Morse code about what the quantum gravitational data is that he got from inside the black hole, and he transfers it to, I think, the second hand or the minute hand on his watch, using some form of gravitational communication. There's nothing like that that can exist in the universe as we understand it today, but in the bulk universe, the hyperspace universe that we talked about earlier, where there are these extra dimensions, that type of gravitational communication might actually be possible. There are some ways where gravity can actually interact through those different spatial dimensions in a way that could be seen in some format of data that's possible, but the math is pretty complicated, and I can't profess to actually understand it, but apparently that's the deal. So that's where they got that from these multi-dimensional universes where gravitational effects can actually traverse from one dimension to another. But another time paradox that's really interesting to think about in these scenes is that all these messages that he's sending back to the past could have only happened if he actually went on this journey. So if that message about, you know, his daughter trying to convince him to stay actually worked, he couldn't have actually sent that message in the first place. So it's all sent in vain. He realizes that at the end and finally sends the quantum data to his then older daughter. But like I said, those time paradoxes are possible with wormholes if they actually turn out to exist. The other interesting thing to point out about wormholes is just how they would appear if we actually saw one. So typically when you see images of wormholes portrayed in diagrams, they look like these funnel shapes. So you got like this kind of rip in space-time, and this funnel appears between two different parts of space-time. So that's basically a three-dimensional representation in 2D. If we were to actually see a wormhole, it would look spherical. And they actually did a really good job of portraying that in the movie. I'll bring up an image of that for you. Hopefully you can see it now. So you can see their rotating spacecraft about to go into the wormhole. And that's actually probably what it would look like. It would be this, this giant sphere, depending on its actual size, and space would be warped around it, huge areas of space. And as you passed into it, that space would fly past you around the curvature of the wormhole. So let me actually show you this little video that I have that depicts what that would look like if you were falling into a wormhole. Bring it up in just a second for us here. Start the screen share again. So this video I'm going to show you is silent, but it gives you a really good idea of what it would actually look like to fall through a true wormhole that was out by the planet Saturn, like they had in the movie. And this simulation was actually created by one of Kip Thorne's students using Kip Thorne's equations. And so it probably is both accurate and precise. So here we go. We'll start getting closer to Saturn, and eventually we'll enter a wormhole here. So now he's zooming back out, and now we'll go back into it. So you'd see the other end of the wormhole as you approached it. Now we're looking back through the other end of the wormhole from the other side. All right, I've got a bunch of other videos that that I can show you that talk about black holes and wormholes, as well as other interesting phenomena about the universe. But I'm curious if anybody has any questions about any of the stuff that we've talked about so far before I bring up one of these videos.
Yes. Can you explain again the concept of the Tesseract in this film? Of course, there is a Tesseract in the Marvel world also.
Yeah, slightly different. The Tesseract in the Marvel world is this this small object, which I believe is the Time Stone, or not the Time Stone. One of the 5 sacred stones in the Marvel universe.
It's like a Power Stone, but
Power Stone. Yeah, Power Stone. Yeah. That's right. Thanks. It's great that the name got popularized. It's actually the shape of that object that resembles something of what a Tesseract actually is. Can you see that new page I just brought up?
Yeah, I was just looking at it myself on my phone.
Yeah, so basically a Tesseract is to a cube as a cube is to a square. It's the next spatial dimension up from a cube. And as we were talking about before with the bulk universe, objects like this might actually exist, but we don't have access to them. But yeah, the Tesseract is a real mathematical multi-dimensional cube.
Right. But in this film, it is a time.
Yeah, so they actually have the dimension of time laid out physically. So just like traversing left to right, up, down, you can traverse all the events of your life in these this multi-dimensional space that they call a Tesseract. And yeah, that might actually be what this universe is like. We don't know.
But it was more than just time, because then the Tesseract has to give him ability to communicate with this planet called Earth somewhere else in the universe.
Yeah, and that's the part that's just real science fiction. Even though he may have had access to all of the events in his life, how that was actually then communicating with Earth instantaneously through the spatial dimension of time is a bit of a stretch. But with any sufficiently advanced technology, as Arthur C. Clarke once famously said, it's indistinguishable from magic. And so in Hollywood, magic becomes reality. So that's what they did there for us. I want to show you just a few minute film about wormholes, because I think they do a fantastic job at describing both the original formulation of wormholes and some of the more nuanced version of wormholes from string theory. This is another one of my favorite websites to learn about science. I don't know how to pronounce this word correctly in German, but it means in a nutshell. And they do an outstanding job in describing scientific concepts. And this one about wormholes is no exception. So it's, I think it's just under 9 minutes before the credits start, and worth watching because it's so relevant to what we're talking about right here.
If you saw a wormhole in reality, it would appear round, spherical, a bit like a black hole. Light from the other side passes through and gives you a window to a faraway place. Once crossed, the other side comes for the interview, with your old home now receding into that shimmering spherical window. But are wormholes real, or are they just magic disguised as physics and maths? If they are real, how do they work, and where can we find them? most of human history, we thought space was pretty simple. A big, flat stage where the events of the universe unfold. Even if you take down the set of planets and stars, there's still something left. That empty stage is space, and it exists, unchanging and eternal. Einstein's theory of relativity changed that. It says that space and time make up that stage together, and they aren't the same everywhere. The things on the stage can affect the stage itself, stretching and warping it. If the old stage was like unmoving hardwood, Einstein's stage is more like a waterbed. This kind of elastic space can be bent and maybe even torn and patched together, which could make wormholes possible. Let's see what that would look like in 2D. Our universe is like a big flat sheet. Bent in just the right way, wormholes could connect to very, very distant spots with a short bridge that you could cross almost instantaneously, enabling you to travel the universe even faster than the speed of light. So, where can we find a wormhole? Presently, only on paper. General relativity says they might be possible, but that doesn't mean they have to exist. General relativity is a mathematical theory. It's a set of equations that have many possible answers, but not all maths describes reality. But they are theoretically possible, and there are different kinds. The first kind of wormholes to be theorized were Einstein Rosenbridges. They describe every black hole as a sort of portal to an infinite parallel universe. Let's try to picture them in 2D again. Empty space-time is flat, but curved by objects on it. If we compress that object, space-time gets more curved around it. Eventually, space-time becomes so warped that it has no choice but to collapse into a black hole. A one-way barrier forms, the event horizon, which anything can enter, but nothing can escape, trapped forever at the singularity at its core. But maybe there is no singularity here. One possibility is that the other side of the event horizon looks a bit like our universe again, but mirrored upside down, where time runs backwards. In our universe, things fall into the black hole. In the parallel universe with backwards time, the mirror black hole is spewing things out a bit like a Big Bang. This is called a white hole. Unfortunately, Einstein-Rosen bridges can't actually be crossed. It takes an infinite amount of time to cross over to the opposite universe, and they crimp shut in the middle. If you go into a black hole, you won't become the stuff coming out of the white hole. You'll only become dead. So, to travel the cosmos in the blink of an eye, humans need a different kind of wormhole, a traversable wormhole. If string theory, or one of its variations, is the correct description of our universe, then we could be lucky, and our universe might even have a tangled web of countless wormholes already. Shortly after the Big Bang, quantum fluctuations in the universe at the smallest scales, far, far smaller than an atom, may have created many, many traversable wormholes. Threaded through them are strings, called cosmic strings. In the first billionth of a trillionth of a second after the Big Bang, the ends of these tiny, tiny wormholes were pulled light years apart, scattering them through the universe. If wormholes were made in the early universe, whether with cosmic strings or some other way, they could be all over, just waiting to be discovered. One might even be closer than we realize. From the outside, black holes and wormholes can look very similar, leading some physicists to suggest the supermassive black holes in the center of galaxies are actually wormholes. It will be very hard to go all the way to the center of the Milky Way to find out, though, but that's okay. There might be an equally extremely hard way to get our hands on a wormhole. We could try to make one. To be traversable and useful, there are a few properties we want a wormhole to have. First, it must obviously connect two distant parts of space-time, like your bedroom and the bathroom, or Earth and Jupiter. Second, it should not contain any event horizons which would block two-way travel. Third, it should be sufficiently sized so that the gravitational forces don't kill human travelers. The biggest problem we have to solve is keeping our wormholes open. No matter how we make wormholes, gravity tries to close them. Gravity wants to pinch it closed and cut the bridge, leaving only black holes at the ends. Whether it's a traversable wormhole with both ends in ours, or a wormhole to another universe, it will try to close unless we have something propping it open. For very old string theory wormholes, that's the cosmic strings job. For man-made wormholes, we need a new ingredient: exotic matter. This isn't anything like we find on Earth, or even antimatter. It's something totally new and different and exciting, with crazy properties like nothing that's ever been seen before. Exotic matter is stuff that has negative mass. Positive mass, like people and planets and everything else in the universe, is attractive because of gravity. But negative mass would be repulsive. It would push you away. This makes a kind of anti-gravity that props open our wormholes. And exotic matter must exert enormous pressure to push space-time open, greater even than the pressure at the centers of neutron stars. With exotic matter, we could weave space-time however we see fit. We may even have a candidate for this exotic matter, the vacuum of space itself. Quantum fluctuations in empty space are constantly creating pairs of particles and antiparticles, only for them to be annihilated an instant later. The vacuum of space is boiling with them, and we can already manipulate them to produce an effect similar to the negative mass we're looking for. We could use this to stabilize our wormholes. Once we're keeping it open, the ends would start together, so we'd have to move them around to interesting places. We could start by wiring the solar system, leaving one end of each wormhole in orbit around the Earth. We could fling others into deep space. The Earth could be a wormhole hub for a vast interstellar human civilization spread over light years, but only a wormhole away. However, wormholes have a dark side. Even opening a single wormhole kind of breaks the universe in fundamental ways, potentially creating time travel paradoxes and violating the causal structure of the universe. Many scientists think that this not only means they should be impossible to make, but that it's impossible for them to exist at all. So for now, we only know that wormholes exist in our hearts and on paper in the form of equations. We know you want to know more about universe stuff, so we're trying something new. Kurzgesagt and Brilliant are collaborating on a 6-part video series about our favorite science and space things. Thanks to their help, there will be more videos on this channel in the next 6 months. Kurzgesagt has worked with Brilliant for a while now, and we love what they're doing. In a nutshell, Brilliant helps you to get ahead by mastering maths and science skills through actively solving challenging and fascinating problems. To support our collaboration with them, visit brilliant.org/nutshell and sign up for free today. The first 688 people that use the link will get 20%.
All right. So, down to our last few minutes. So I just want to see if anybody else has any questions about any of the scenes in Interstellar or anything that we've already talked about.
First of all, Sam, this is Matt here. That video is really cool. Thank you for sharing that.
Yeah, those guys, great. They do an awesome job.
Super cool.
Yeah, I need it dumbed down a little bit for me, you know?
Yeah, they do get into some complicated stuff, but for the amount of stuff that they're covering in 9 minutes, I think they do a pretty good job.
Yeah. Yeah, I just wanted to chime in and say at least, hey, we've really been enjoying it over here, so thank you.
Thank you, Sam.
You're so welcome.
Yes, thank you, Sam. This is great.
Yeah, you're very welcome. Any other?
I think there are no questions because it's so complicated.
Yeah, yeah, it's bizarre stuff. So the last thing I wanted to ask all of you is there a movie that you'd like me to tackle next time? Some favorite sci-fi movie that you'd like to dissect?
Spaceballs.
Spaceballs?
There's got to be some quality content in there. Come on.
Yeah, I mean, I think they've got the warp drive.
They've got the warp drive. They've got the literally jamming the radar.
That's right. Yeah, that would be fun. I haven't watched Spaceballs in a really long time, so that sounds like a fun homework assignment.
An RV that flies through space.
That's right. Cool stuff. Okay, well, we'll do Spaceballs next week.
Yeah.
Now we have our homework.
Yeah,
And
so everyone, y'all have to watch Spaceballs, and then we'll dissect it next Tuesday.
I'm just throwing that out there. I'm open to it.
Well, I'll see if we get any other suggestions. Feel free to email me if something comes to mind in the next several days.
Actually, Sam, I love the movie Contact.
Oh yeah, that would be, so it's interesting.
Yes.
So
yes,
the movie Interstellar is not the only movie that's ever dealt with time dilation or with wormholes. And the movie Contact is another one. And in fact, I think that the wormhole that they use in Contact is probably more scientifically accurate than the one they did in this film, Interstellar. So yeah, that would be a really fun one.
Yeah, let's talk about that one.
Okay, yeah, and again, that was a brainchild of another astrophysicist. That was Carl Sagan, one of the greats.
Mm.
So that would be a lot of fun. Yeah, let's do Contact
And Spaceballs.
and Spaceballs. We'll do Contact next week, and then we'll do Spaceballs after that.
Okay. Yeah, when things get really rough.
All right. Well, any questions about Interstellar? Any resources you'd like to think about it some more, or anything like that?
I think I will say, if we are going to send someone around the universe, Matthew McConaughey, he's not the worst choice.
Yeah, I must say that I love the movie Interstellar, and I was actually pretty forgiving of all of the science in it until he came out of the black hole. I was really hoping that his character was going to be a martyr, fall into the black hole, and that would be sayonara. But then, the information could get transferred somehow, but that he would die in the black hole. So the fact that they brought him out of the black hole was a little bit too much for me. But Hollywood.
All right.
You have to permit a lot of poetic license.
Yes, that is true.
Yeah. You have to forgive a little bit.
Yeah, it was a beautiful cinematic film, so I was psyched the way they did that.
Yeah, and complicated.
Yeah.
Well, Sam, thank you so much, man. Thank you. We really appreciate it.
It's my pleasure. Yes. Thanks for tuning in.
From Sam and I.
Thank you.
Cheers, guys.
Have a good evening.
Yeah, good night, guys.
Good night. Thank you.
See you later.
That's so cool.